Okay, so now we're going to talk about vectors. You're going to find out vectors, we use a lot of vectors in physics. Whenever you do forces, whenever you do, things that, like velocity, acceleration, all this quantity are vectors. So you need to know how to operate vectors. And so in this chapter, you're going to learn the difference between vectors and scalars. You're also going to learn how to sum vectors together, and also how do you resolve the vector. In other words, you want to find the components of a vector, and you want to express vectors in unit vector notation. And you're going to also learn, the angle magnitude notations of a vector, and also the scalar product, and also the cross product. Okay. So what exactly is a vector? Now last time we mentioned that vector comes with the magnitude and direction. So let's say you have the vector that's pointing, let's say it is pointing in this direction. Okay. So you have a vector here. So we can the vector. So you have the end here and the arrow. The arrow indicates the direction, and the length indicates the magnitude. So one other thing about vectors is that, the vector, it doesn't really matter where you place the vectors, as long as it has the same length, as long as it is, pointing in the same direction. Then we call, they are the same vectors. So in other words, you can have a vectors here. Now, if you move the vectors, let's say place it somewhere, and then still maintain its same length and also direction, let's say if you move it over here, okay, they have the same length and then same direction. These two vectors are the same vectors because they have the same length, they have they're pointing in the same direction. So that's that's a characteristic of a vector. All right. Now let's say we mentioned that displacement is a vector. Take for example, let's say this is point A and this is point B. Okay. And then you walk from point A to point B. It may not be in the form of a straight line. You might walk somewhere and some here, and then come to your final destination. So this is your starting point, and this is your final point. And in order to find the displacement, we know that it is a final position minus the initial position. So you can express this displacement in vector form. So in other words, it is just between this point A and point B. So we can draw a straight line and then use this arrow to indicate it is from point A to point B. So we can see that regardless how you walk from point A to point B, when it comes to the displacement, it just it's just from point A and point B, a direct straight a straight line connecting these 2 points. Okay. So how about if you had, so this is your starting point and this is your final point. So only the initial and the final point that are important. It doesn't really matter how you go from here to there, as long as it's have the same starting point and the end points. Okay? So this is what we call vectors, which comes with the magnitude and direction. Now what about scalar? For scalar, basically they just have magnitude. They do not have a direction. Okay? So that's the difference between the vector and the scalar. Now let's say if you want to have A plus B, so you have the vector A, and then let's say this person walked from point B to another point, let's say point C. So you are going to draw from A to B and then B to C. So you're going to draw from, so the initial point is this point and then directly to point C. Okay, so this is your another vectors. And you can find out what is the net, from point A to point C. How would you find that? So from point A to point C, again, you just directly connecting these 2 points with the arrow. So this is your initial point, and this is your final point. Okay, so you can consider this as this is vector A that's from point A to point B. And this is your vector B, that's from point B to point C. And this is the sum, so your sum is equal to A plus B. Okay, so just directly connecting these 2 points. Doesn't really matter how we get from there. Although you can see that A to B, you have going through this, and then B to C, you might go from here and there. But then when it comes to A to C, just directly connecting these 2 points, starting point, initial, and the final point, and that gives you the vector sum of these two vectors. Okay. So how do we do? So regarding mathematical operation of vectors, here are a few things. Let's say you have 2 vectors, A and B. How do you find the vector sum? And how do you find how are the properties of a vector? So in order to find the sum, so you have, let's say C is, we use S actually. The sum, so it is a vector. When you do the vector sum, you add 2 vectors together. So you have A plus B, and then S, that gives you the vector sum. So it is a vector, okay? And there are also some rules which we call commutative laws. Okay, so you have, so what does that mean? Commutative. If it's commutative, which means that how you add them together really doesn't matter, okay? You can have A plus B, and that's equal to B plus A. So how you add them together, the order does not matter. Associative law, it means that, you can, let's say you have 3 vectors, A, B, C. So you have A plus B. You find these 2, and then add a 3rd vector together. And you can, so you associate A and B first, and then add a 3rd vector C to this vector sum. You can also add B and C together, associate B and C together, and then add the 3rd vector A to the vector sum. So it is the same thing. Okay, they are very basic. Now, what about when you reverse? If you have a vector that's pointing in this direction, what will be the negative of that vector? The negative of the vector would just basically reverse the direction. That keep the same magnitude but pointing in the opposite direction. So in that case, what we have here is that vector B, let's say this is your vector B, and when you reverse its direction, this becomes negative vector B. So when you add them together, as you can see, one is pointing in that direction, the other one is pointing in the opposite direction. So when you add them together, that basically gives you a 0. So they cancel out each other. Okay. So in that case, what about subtraction? How do you subtract one vector from the other? When you do subtraction, let's say we use a vector D to indicate the subtraction. So you can have, let's say your D is equal to, if you want to do the A minus B, so vector A minus vector B, this can be written as A plus and then negative B. Okay? What it means is that because we already know how to sum the 2 vectors, and if you want to do the difference between the 2 vectors, what you need to do is that change this vector and reverse its direction, and then you add these 2 vectors together, and that will give you the vector sum. Okay, so that's basically some of the laws associated with the vectors. Now, how do we add them together? How do we add them together? So basically, let's say you have on this. So if you have vector A, and then if you have vector B, so this is A, and this is B. How would you add them together? So you will place. So if you want to do A plus B, so what you do is that you move vector B, and then because they are the same vector, no matter where you place them, so you move it over here, place a tail to the head of the first vector. So this is your A, and this is your B. You just move this across, and then draw from the tail of A and pointing in the directions of the head of B. Okay, so this is how you do a vector sum. So this is A and B, and then you do it like that. What about if you want to do A minus B? So if you want to do A minus B, so that's A minus B, which is equal to A plus negative B. So your B here now is actually point in the opposite direction. So you have like this. So you have A. So this is your B, and then you're going to have like this. Okay. So basically your A plus negative B will be from this point to this. So this is your negative B. We just reverse the order, and then so now it becomes A plus negative B. So you have from the tail to the head, from the tail of A to the head of negative B. So this is how you do A minus B. Okay? Just by looking at the diagram. So A plus B, so again, whenever you do the vector sum, it is starting from the tail of the first vector pointing to the head of the second vector. This is how you do A plus B. Okay, do vector sum. All right. So these are just basically the characteristics of a vector. How do we do, let's say you have a vector pointing in some direction in the x, y coordinates. How would you resolve a vector to find the x and y component? This is how you would do it. Okay, so let me erase this. So let's say you have on this x and y coordinates, you have the vector A that's pointing in that direction. So let's say you have A, and then it's making an angle theta with the positive x-axis. So how would you find the x and y component? To find the x and y component, what you need to do is that realize that in the x component is the one that you have the projection of the vector A into the x-axis, and your y component is the vector A projected to the y-axis. So we can actually draw a line here. So this becomes a right triangle, okay? And your A here is a hypotenuse, and this is your A, the main to A. So I'll drop in the vector sign. So if the angle is defined as it's defined that measure from the positive x-axis. This is how you do the x and y. This is how you find the x and y component. So your A sub x, the x component, is the vector magnitude A, and then times, this is the angle theta, this is the x component. Whenever that's adjacent to the angle, it is cosine. So it is A cosine theta. And then what about your y component? Your y component is this component, and that's opposite the angle. If it's opposite the angle, then the y component is equal to A sine theta. Okay? So you have your A sub x here, and then you have your A sub y here. So you can see that this is how you resolve the vector. And so very simple. The x component is just A times cosine theta, and the y component is A times sine theta. You can use this expression as so long as your angle is measured from the positive x-axis. If the angle is not measuring from the positive x-axis, then you cannot use that information, and which we're going to discuss. When you have an angle that's given, that's not measured from the positive x-axis, how would you do it? Okay. Now, what about angle? Now, for angle, use trigonometry. We all know that your tangent theta. Your tangent theta basically is the opposite over the adjacent. Your opposite is the y component, and your adjacent is your x component. Okay? So that's basically, you have a vector like that. Now I'm going to talk about another vector that's pointing in the opposite, other direction. For example, let's say I have a vector that's pointing in this direction. So let's say I call that B. Okay? And I'm going to define the angle here. Let's say this is my theta here. So if you have a vector that's pointing in that direction, and you have the angle that is measured from the positive y-axis, how would you find the x, y, and x component and the y component? So again, we're going to draw a line. So this is this is perpendicular to the y-axis. And you're going to find the projections of vector B that to the y-axis and to the x-axis. So if you look at this diagram, you can see that this is basically your x component. And then this, when you draw the line here, that's your y component. So you have the x and y components. The question is, how do we utilize this information to find the x and y components? So in this case, you can see that my angle is defined from the positive y-axis. It's no longer defined from the positive x-axis. So you cannot use this. You cannot use this equation to do the to do the calculation. What you want to do instead is use trigonometry. Okay. So how do we do it? So you will again saying that this component, your bx, is equal to your magnitude b, and then this bx is opposite of the angle. If that's opposite the angle, like I said, you should use sine of theta. So you have bx, that's sine theta. Now, the other thing is that, so you have b and then sine theta. If you look at this component, it is actually pointing to the left, which means that it should be negative. So you should put a negative sign in front of it manually, okay? So when you punch it to a calculator, because the theta here is less than 90 degrees, so when you punch it to a calculator, this will not give you a negative sign. You have to manually put a negative sign in front of it to take, to indicate that it is pointing in the negative x-axis. What about your y component? Your y component is actually now adjacent to the angle. If that's adjacent to the angle, then you will use cosine theta. Okay? And because it's pointing upwards, so you can just leave it like that. So you can see that when you compare this expression to that expression, this s component utilizes cosine theta, but this component actually uses sine theta. And then you have to use a negative sign in front of it. So that's the difference between which angle, this is angle measuring from the positive x-axis, and this is the angle that's measuring from the y-axis. Okay? What about when you want to find this tangent theta? How do you find this angle theta? So in order to find tangent theta, so we do the tangent. So you have your tangent theta. And then again, by definition, your tangent theta is that you have the opposite over the adjacent. So the opposite here, again, is your bx. And the adjacent is your by. So you have that. Okay. Now, the other thing I want to caution you is that we know that bx here is a negative value. So you actually have to put an opposite value of that. So this is, again, another difference. So you can see that the difference between this and that, and also how you measure the angle, they are quite different. So when you resolve a vector, these are the things you have to be a little bit careful. Okay? Which angle are you using? And when you're using, so we can see that when you use small, this is what we call small angle, because angle is always less than 90 degrees. When you use a small angle, you have to manually put a negative sign in front of it. And when you use the small angle, when you want to calculate the angle, you want to use the absolute value of that in order to find the theta. Okay. So you can see that this angle theta is in reference to the positive y-axis. So sometimes you ask to find, okay, what is the angle in reference to the positive x-axis? So in that case, you have to actually add 90 degrees to this angle in order to give you the full angle measuring from the positive x-axis. Okay? So that's the thing that you need to be careful. Now, what about, so this is when you have the vector A, you have the angle. So you can resolve the vector into the x and y component. So how about that say, in a reverse order, you know the x component, you know the y component. What will be the vector A? What will be the magnitude of A? So in this case, you can see that this is just regular right triangle. You have this, the length for both, for both sides. So it's become very easy because your A, we just use a Pythagorean theorem. That will just be square root of the x component square and then y component square. Okay. Likewise, your b value here would just be that the bx squared and then plus by squared. So that's very easy to do the calculation. And again, when you calculate the angle, make sure that use the absolute value when you're dealing with a small angle, and then manually put a negative sign in front of it if your vector is is in the leftward direction or downward direction. Okay? All right, so that is that. Let me see. So we have all this vector that can point in all the directions. So we need to actually, so sometimes, you need to specify, specify the directions of the vector. How would you specify it? So we define, we use a Cartesian coordinate. So this is what we call the Cartesian coordinate. So, on the x and y plane, so you have your x, this is your y. What happens if you're living in a three-dimensional world? You have the z, so where's the z? Your z is coming out of the whiteboard. So let me just draw this. So it's coming out, and this is your z, okay? So, in unit vector notation, this is, in the x direction, we call that I hat. It has the directions of x, positive x-axis. It has a unit of 1, okay? What about y? In the y, we use j hat. So again, the length is 1, and it is j hat, pointing in the directions of the y-axis. And then you have this, what we call the z, and then we call that k, okay? So you can see that you have your I, j, k that indicate the x, y, and z direction for for a vector. So now you can actually we have the ax here, we have the ay here. So you can express this vector in unit vector notation. And so I'm just going to write it here. So in this case, your vector A is equal to ax, x of x, and which is positive, so you have I hat, and your y, and the y component is also positive, so you have plus a sub y and then j hat. So this is your vector A that has the x and y components, okay? And then they both are in the first quadrant, so they are, they are all positive. Now, what about your B? So your B here, you will have the bx. So you have the bx, which has this. So I'm just going to write it out so that you can appreciate that, this is, so you have a negative b, and then sine theta. This is your x component, I hat, and the y component is positive, so it's plus b, and then cosine theta, j hat. So this is how you express vectors in unit vector notation. So you can see that, to express vectors, there are two ways. One is unit vector notation, and the other one is magnitude-angle notation. So both ways will work. Most of the time, we'll be dealing with the unit vector notation. So once you find the x and y component, and just affix the I hat and j hat to give it a direction. So you can express those in unit vector notations. Okay. All right. So it's very easy to use with the unit vector notation. Now, so let's say you have vector A and vector B. How did you find, let's say, vector sum? Let's say we have a vector R that's equal to A plus B. So how would you do that? So again, if you're doing the, if those vectors are in unit vector notation, you can just base it like that. Let's say I'm going to write it out here. So you have the x component, I hat, and then y component, j hat. So this is a vector A. And you have the vector B also in unit vector notation. So you have the x component, I hat, and the y component, j hat. So when you want to find the sum, we say that, okay, your R is equal to A plus B. So what you're going to do is that you're going to add all these numbers together, so long as they are in the same direction. You don't cross add them together. You add all the numbers in the same directions together. So in this case, you have your a sub x plus b sub x. They're all x component, and that's your I hats. And then you're adding all the y components together. So you have ay plus by, and that's your j hats. Okay, so you can identify this. So this is your Rx. Your Rx basically is the sum of the x component, and you have your ry, that's the sum of the y components. So your r is equal to your rx I hat, and then it's getting very busy, so let me just erase that, and then ry j hat. Okay, so once you have the vector sum, and then you find out the x component and the y component by adding the components together, now you have the x and y components. So how would you find the magnitude of r? So in that case, again, if you have x and y, then that becomes very easy because your r would just be the you square each individual one, and then you add them together, and then take the square root of the sum. So you have the x component square, and then plus the y component square, and you take the square root of the sum. So that gives you that. And how would you find the angle of this vector? So whenever you want to find angle of that vector, my suggestion, and I strongly recommend you do that, is that once you find out the numerical value, then you want to draw it on the x or y plane to see which quadrant that the vector is pointing. Take, for example, let's say we have your r, and now r is pointing, so let's say we already use the first and second, let's say we have the third quadrant. Okay, so your r is actually pointing in that direction. And you have the rx. So this is your x component. Okay, so let's say this is your r, and then this is your y. So you have the y component, and then both are negative. So in that case, how would you find the angle? So again, once you know where your vector is pointing, then you need to define your angle before you proceed to find your angle. That's it. We define this to be our angle theta. So in that case, how would you find the angle theta then? So you use tangent theta. So again, you can see that I'm using smaller angle because it's less than 90 degrees. I'm not measuring from positive x-axis. So in that case, you can have this. So you have the use absolute value, and then in the numerator, it is opposite the angle. So this is your y component, and then in the denominator, you should use the adjacent one, which is the x component. So when you do that, you can have an angle, whatever that is. And then, so finally, the answer will be that you add 180 degrees to the angle in order to get, let's say, your theta prime. Okay? So this is the angle of the vector, theta prime. So your theta prime here is equal to theta and then plus 180 degrees. So that's why whenever you do vectors, you want to draw the vector on the x and y axis in order to know which quadrant that the vector is pointing, because for different quadrant you will have a different numbers, and then you're going to either add 90 degrees, 180 degrees, or 270 degrees. It really depends on which quadrant that the vector is pointing. Okay. So this is when you do the vector sum. When you want to find out the difference, then it's also the same. So let's say if you have the a and b, and you want to find b minus a. How do you do that? So let's say your c here is equal to b minus a. Then all you need to do is that use the s component, and then subtract the s component of a from the x component of b. So you have the bx minus a sub x. This is I hat, and then plus the by minus ay, and then j hat. So you can see that your s component of c is this, whatever numerical value that you have, and your y component of c is this. And once you have the x and y components, and then you can use the Pythagorean theorem to find out your c. To find the angle, again, plot it on the x and y axis to see which quadrant it is, and then find your theta. Okay? So those are the simple math, how to find the angle, how to find the component, when you have the vectors and stuff. All right. So another thing we want to talk about is that when you have the Cartesian coordinate, you have the x that's pointing horizontally, you have the y-axis that's pointing, that's perpendicular to the x-axis. So what if I have another coordinate system that's not pointing in that x and in the traditional x and y direction? So in that case, how would you express the same vectors? All right. So let's say we have x and y axis. This is my x and y. And we have a vector, okay, that's pointing in this direction. So that's a vector A. And it is making an angle theta with the positive x-axis. Now, we have another coordinate system that it is actually being rotated. So let's say you have your x that's x prime. That's called x prime. The coordinate system that's in this direction. So this is your x prime. Now your y prime, of course, is the one that is perpendicular to your x prime. So this is your new. So this is the one in blue are your new coordinate system. So if you look at this vector A is defined, according to the old coordinate system. Now, when you have a new coordinate system, how would you express your vector A? I'm just going to draw this a little bit longer so that you see that the projection. So now you can see that the angle between vector A and the new x axis is no longer theta. You will have another angle that's called that theta prime. So in that case, this is your theta prime. And you can see that the difference between theta and theta prime is this angle. Let's say that's C. Okay? So in that case, let's look at how we express this vector in two different coordinate systems. So in the black, in the old coordinate system, your A. Where's the cap? Right. Anyway, so let's look at with using the traditional x and y axis. Your A here, you have the s components, and then you have your y component. I'm sorry. So this is your s component, and this is your y component. So your A here would just be that you have the x component square plus the y component square, and that's your that's your A. And your tangent theta. So your tangent theta here would be that your tangent theta. What would be your tangent theta? Your tangent theta using the black, so that will be the opposite, which is AY over the AX. Okay. Now let's look at the one. If we want to express vector A in the new coordinate system. First of all, the angle between vector A and the x prime is theta prime. So you need to find a projection. So this is actually the projection. This is your y component. Okay, and then your s component. Your s component is this. So that's your s component. Okay, so I'm just going to use prime to indicate that that's a new express that in a new coordinate system. So you can see that your ax and ax prime are not identical. Your ay and ay prime, they are not identical. What's identical is that this is the same vector. It's just being represented by different coordinate system. So if we look at our the main two, so the main two, if you're using the ax prime and the ay prime, so you can do that. So your ax prime square plus ay prime square. You still have the same vector. The only difference is that your ax prime is not equal to ax. Your ay prime is not equal to ay. But then the main two itself is still the same, as you can see from this diagram. Okay, the main two still is the same. What about the angle theta? So the angle theta prime, so you can find out theta prime. Your theta prime is basically equal to the y component. So your y component is this. So you have your ay prime and then over the ax prime. Okay, and how are we relate the angle theta and theta prime? you can see that the angle between them, they differ by angle c. So you have your theta, which is this from the old system. So theta is equal to theta prime, and then plus the difference between them. That's how you relate this two coordinate system, the new system and the y system. Okay. All right. So these are just the basic operational vectors. Now the next two things I want to talk about is about when you have two vectors. We've done we've done the situations that when you have two vectors, when you add them together, how do you add them? When you want to find the subtraction, when you want to find the difference between two vectors, how do you find it? What about vector products? There are two different kinds of products. One is called the scalar product or the dot product, and the other one is called the cross product or the vector products. So these two products are very important in physics because a lot of concepts, a lot of quantity utilize the vector product. Okay, so the scalar product, which we also call that dot product. We call that scalar is because when you have two vectors in the initially, when you do the scalar product, you'll find that they, after the scalar product, they become a scalar. So you have two vectors doing the scalar product, it becomes a scalar. So let's say A and B. If we want to do a scalar product, then we put a dot there. So between them, so A dot B. A is a vector, B is a vector. After you do this, dot product, what you're going to have is that you have the value of A main to A and then main to B, and then times the angle between them. And the angle, let's say the angle between them is C. So you have, let's say, this is your A, this is your B, this is the angle between them. So scalar product is just basically very simple. A times B and then times cosine the angle between them. So we usually use scalar product to calculate work. What you're going to learn, work is basically the scalar product of force and displacement, or even power. So the power is, one of the expression for power is the scalar product of force times the velocity. Okay. So if you look at this, basically, if you use the associate, associate law, you can see that you can express this as A times B cosine C. This also equal to A cosine this, and then times B. What does that mean? It means that, when you do a scalar product, you're just finding the component that's projected to the second vector. So in this case, if you want to do, let me draw the extension line. So if you want to do A dot B. So if you keep your A, then you draw a line here. So what you want to do is that you can, let me just draw a line. So you can, so this, if you do a projection, this is your B, and then the A, when you project, this is acting as a hypotenuse. So the projection onto the B direction will be that will be A times the angle between the angle adjacent to the angle, so that will be this. So when you do the product here, that becomes AB times cosine C. Okay, or you can do actually find the use your B as a hypotenuse, draw a line, and that's perpendicular to this. So you'll have the A, okay, and then times the projections of B. So this is the projection of B. This is main to B. And then times the, because it's adjacent to the angle, so cosine C. So you can see that they are exactly identical. It's really depends on how you interpret it, whether you find the projection of A or find the projection of B onto the other vector. Okay. So what it means is here is that A dot B is equal to B dot A, as you can see. Okay. So that's basically that. Now, this is when you do that. What about if your vector A and B? This is when they are expressing, angle magnitude notation. What about if you have A and B that both are expressing the unit vector notation? How would you find the A dot B? So to do that, this is how you would do it. So let's say A has X component, Y component. Your B has X component and Y component. So when you do A dot B, the only thing that survives is the I dot I. So I dot I give you 1. I dot J give you 0. So these are the principle. So when you have that, so when you do I dot, so when you multiply them together, so let me just write it out. So you have AX I hat plus AY J hat, scalar product of BX I hat, BY J hat. When you do a scalar product, so you can see that the first term, so you have to multiply them out. So I dot I, that gives you 1, so you have your AX, BX. Okay? Now, when you multiply AX I hat and then times the scalar product BY J hat, I dot J is equal to 0, so that has no contribution. Likewise, for this one, AY times BX, because you have J dot I hat, that also gives you 0. And then the only term that survives is AY times BY. So it's plus AY times BY because J dot J, that gives you 1. So you can see that in Euler vector notation, your A dot B is equal to AX BX plus AY BY. And then if you extend it to the three-dimensional, then you have all the X components plus all the Y components and then plus all the Z components, as you can see. Okay? And it's just like two numbers multiplied in together. So this is the scalar product. Now the other product that you're going to use a lot is what we call the vector product. Or cross product. When we say vector product, it just means that after you multiply them together, they are still a vector. So for example, you have vector C, let's say vector C is equal to A cross B. So instead of using a dot, we use cross. So A cross B, that is that. So how would you find the magnitude? So C is equal to, again, the magnitude of A, the magnitude of B, and then sine of the angle between them. So instead of cosine, now it's sine of the angle between them. Okay, so you have the vector A and vector B. So how would you? So I'm going to use this. So how do you do vector A and B? So let's say this is angle theta. So you have A cross B. Now, when you do the cross product, direction, who comes first becomes very important because A cross B is actually equal to negative B cross A. So you have to make sure that, when you do that vector product, it is the order actually is important. So how do we find A cross B? So this only give you, AB sine theta only give you the magnitude. What about direction? To find the direction, then you want to use your what we call the right-hand rule, okay? And then you're going to use this vector product a lot, especially when it comes to finding the torque, okay, or the angular momentum. All this involves a vector product. So how do we do a vector product? So this is how you do it. A is the first vector. So you want to point your fingers in the directions of the first vector, and then sweep your finger toward the direction of the second vector. Take for example, this is your A. It's pointing right, to the in the opposite x-axis. This is your B. That's off the angle, and then so you want to point your fingers in the same directions of the first vector. Sweep your finger toward the second vector, and your thumb gives you the directions of the vector C, the third vector. And you can see that this is basically forming an X and Y, Z plane, and your thumb is pointing out of the whiteboard. Okay, so A cross B. So your C is, if you want to express that in Euler vector notation, that will be this, and then your positive K hat. So your I cross B, and then this thumb gives you a k-hat. Okay, so this is basically how you would do it. Now, when you have the vector product, what we found is that I cross j is, so let's say this is your x and y, and this is your z pointing outward. So I, j, and then k. So use our right-hand rule, I cross j, that gives you, that should be pointing outward, okay, but it's kind of difficult to draw it, so just use your imagination. So you have I cross j, that is positive k hat, okay, and then when you have j cross k, that gives you I hat, and then when you have the k cross I, when you have k cross I, so k cross I, that gives you j hat, okay? So you can see that I cross j, that's equals to k hat. Now, if you have j cross I, that gives you negative k. If you have k cross j hat, that gives you negative I. If you have I cross k, that gives you negative j. And this is basically how you would do it, okay? So what it means is that you have a cross b is equal to negative b cross a. So that's why I said that, when you have a vector product, the order of the product is important because it differs by a negative sign. Okay. Now, how would you so that's how would you do a vector product when your vectors are given in unit vector notation? So you have axi hat plus ayj hat, and then cross product bx I hat plus bj y hat. So again, these are the principle to go by. I cross j give you k. What about I cross I? I cross I give you 0. And likewise, this is I. J cross j give you 0, and k cross k that k cross k that gives you 0. Okay, so in other words, you can't have a vector that's pointing, do a vector product in the same direction. If you, that will give you 0. So in that case, let's see. We multiply them out. So you have ax, bx, then you have I cross I. That's your first term. So I'm going to actually write it out, just so that you have a better understanding. And then the second one is ax, by. You have the I cross j. Okay. And then the third term is that you have ay, bx, j hat cross I hat. And the last term is ay, by, j cross j. So immediately you can see that I cross I has no contribution. J cross j, no contribution because it gives you 0. Now, I cross j, that gives you k. So you have your ax, by, that's k hat. And then you have j cross I. J cross I, let's say j cross I, that gives you negative k. So you have negative, and then ay, bx, and then k hat. So the final result is you'll have ax, by minus ay, bx, and then k hat. Okay? So when you have the cross product, so basically what you see here is that you have your s component times the y component, and then this y component times the s component of the second, and then there's a negative sign in front of it. Okay. So that's basically how you do the vector product, and so this concludes the things important from chapter 3.